All right. Well, now I'd like to analyze something called thermal therapy, which uses magnetic nanoparticles to help treat diseases like cancer. Here, 1 second. Well, here's the idea behind nanoparticle-assisted thermal therapy. We imagine a patient is injected that has a tumor is injected with magnetic nanoparticles. And through some mechanism, the nanoparticles target the tumor. They accumulate here. All right? Then the nanoparticles are heated up. And this is quite interesting. So these are magnetic nanoparticles, and they're heated up by exposing them to radio or microwave frequency electromagnetic radiation. So in the microwave radiation, there's an oscillating magnetic field, right? This is an electromagnetic wave. So there's a high intensity oscillating magnetic field. And the nanoparticles, they're like little magnets. They want to line up in the magnetic field. And so they do this, but because the magnetic field is oscillating, they're constantly flipping over and over and over again as the field oscillates. So energy is being kind of deposited into these nanoparticles to make them rotate. And over time, they give up this energy to their surroundings. So much like a microwave oven, but at a lower frequency and all of that, these magnetic nanoparticles are taking up the energy and then um, that eventually becomes heat that heats up the surrounding tissue. All right? So that's nanoparticle assisted thermal therapy. And the idea is that by doing this, we can locally heat up just the tumor inside of the patient. And if one can heat the tumor by 5 to 7 degrees Celsius and hold it at that elevated temperature for a little while, then the excess heating will destroy the tumor. It will kill the tumor cells. Of course, the goal to this is to heat only the tumor and not heat up the surrounding tissue and cause damage to healthy tissue. So that's the trick that we need to master in order to use thermal therapy. Thermal therapy is a big deal. This is an active way of treating cancer. And so there are lots of companies, medical companies, that make magnetic nanoparticles for this purpose. Here's the top 10 companies listed here. American Elements, here's Merck, here's Thermo Fisher Scientific. I have a piece of equipment from them in my lab, and on and on. All right, so this is big business. So here, let's take a look and see if we can figure out how this works. Okay, now in order to talk about this, we have to add one more piece to what we've learned. So far, we've talked about the cooling problem, okay? Here, all right, where heat uh, is transferred out of our nanoparticle, say, into the surrounding tissue. So we know how that works. What we have to add is this, the absorption of power from the microwaves. So suppose we have microwaves with some incident intensity phi in watts per meter squared. Okay, so that's power per unit area. And that's incident on a nanoparticle. The nanoparticle has some absorption coefficient, alpha, and it also has some volume. Alpha determines what fraction of the incident microwaves is taken up per unit volume. And well, of course, the volume tells us the total amount of power. So the amount of power that's absorbed by the nanoparticle, we'll call that P sub A, is equal to phi times alpha times V. It's equal to the intensity of the microwaves times their absorption coefficient times their volume, of course. So the bigger the nanoparticle, the more power it will absorb. All right? On the other hand, the heat flow from the nanoparticle is described with this equation, which we've already looked at. All right, now let's turn to the notebook and see if we can learn what the scaling laws will look like for this problem. All right? Hang on 1 second. Okay, here let's look closely at one aspect of thermal therapy. In thermal therapy, we're heating up these nanoparticles in an effort to heat up a tumor that's embedded in normal tissue. And we want to confine the heating as much as possible to the tumor. So we want the tumor to be hot and the surrounding tissue to be cooler. And that means we want to maximize the delta T over delta X. That is, we want to maximize how fast the temperature changes from hot to cool as we move away from the nanoparticle. All right? We have to put in radio frequency power to heat up these nanoparticles. We want them to absorb strongly so we don't have to use too much power into the patient to get the nanoparticles to heat up. And then we want the nanoparticles to dump their heat into the surrounding tissue. And we want the heat to move away at just the right rate so that the tumor heats up a lot, but the surrounding tissue not so much. Here, let's see if there's a kind of scaling law that describes that. Hang on. Okay, so to look at this, let's just summarize what we found. So we know that we've said that when the nanoparticles are heated up, that the rate at which heat energy is transferred into the nanoparticle, the absorbed power, is given by the intensity of the microwaves times the absorption coefficient for the nanoparticles, that just depends on what they're made out of, times the volume of the nanoparticles. We have twice the volume, then of course we absorb twice the power. On the other hand, the nanoparticles cool off by transferring heat to their surrounding tissue, and the power out is given by Fick's law, minus thermal conductivity times the surface area of the nanoparticle times Tt dx. Okay? It's driven um, by the thermal gradient, delta T, delta X. Okay, once again, we'll find that we can discard a lot of the details when we analyze the problem to find a kind of a scaling law. The first thing we're going to do is we're going to assume that we're in steady state. That is, we've turned on the heating power and everything has heat has started to flow in. And after a while, we reach a steady state where power is constantly being absorbed by the nanoparticles and it's constantly leaking out to heat up the surrounding tissue. In steady state, the power transferred out of the nanoparticles is equal to the power transferred into the nanoparticles. So PT is equal to PA. And so that means that minus Ka delta T delta X is equal to it's equal to phi times alpha times V. All right? Okay. And so that means that delta T delta X can be written as phi times alpha times B divided by K, times A. There we are. Oh, and there's a minus sign. The minus sign just tells us that as we um, move away from the nanoparticles, the temperature goes down. That's all that means. All right? And we want the magnitude of this term to be as large as possible. All right? But notice something. Delta T, delta X, the change in temperature with position is proportional to V over A. And that means it's proportional to the characteristic dimension cubed divided by characteristic dimension squared. And so it's proportional to D. Okay? So there is a scaling law. We can maximize this temperature differential, which tells us how much we can heat the tumor without heating the surrounding tissue too much by maximizing the size of the nanoparticles. There's actually a trade-off here. We want to maximize D, oops, to maximize this temperature contrast, dT/dx. But it turns out there's a countervailing pressure. Later, we'll see that if we minimize D, we can maximize how well they couple to the incident oscillating magnetic field from the microwaves. So there's a trade-off between these. And there's an optimum nanoparticle size that's not too big and not too small to have effective thermal therapy. But it's interesting. Originally, people thought, well, the smaller the nanoparticles, the more nano they are. So those must be the best for thermal therapy. And actually, it's a scientist, a friend of mine over at the University of Minnesota, a biomedical engineer named John Bischoff. His group showed that no, actually, you didn't want them to be too small or else thermal therapy wouldn't work. Okay, well, that was the second example I wanted to talk about. So we found that the cooling rate for objects depends on their size, and it obeys a scaling law. Excuse me. The smaller the object, the faster it cools. All right. And then we looked at an interesting application called thermal therapy and found in that case there's another trade-off, which means we can't make the nanoparticles too small for this particular application. All right, let's stop here, and I'll see you in class.